Our topic today is volume and area of spheres. Now it's probably easiest to think about a sphere if you think about a ball. Now, this isn't a real soccer ball, it's actually a pencil holder, but let's assume it were a soccer ball. If you're thinking about the volume of our soccer ball, you would be thinking about how much air it would hold. If you were thinking about surface area, you'd be thinking about how much leather it would take, or plastic, it would take to make that ball. Okay? So that's what we're talking about when we're talking about a sphere. Okay? Oops. Anyway, we're talking about volume and surface area. So the easiest, now this is fairly complicated if you're trying to figure out why the formulas work, but if you think about, maybe you could think about this ball inside a cube, and what sort of part of the space in there would it take, would it fill up, or what sort of portion relationship would the area of this cube be to the area of the sphere. So here are the two formulas that you need. The first is surface area. The surface area of a sphere is equal to 4. It's round, so it's got to have pi involved somewhere. 4 pi r squared. Remember, it's squared because we are talking about area, two-dimensional. Volume, very similar looking formula, only it's 4/3 pi r cubed. Again, remember it's cubed because we're talking about 3 dimensions. Okay? Let's use an easy example. Let's say that we have a sphere, and our sphere has a radius of 6 meters. Okay? 6 meters. How do we figure out the surface area? Well, we're going to start with our formula, which is 4 pi r squared. Okay? We're going to say surface area is equal to 4 times pi times the radius, which is 6 squared. Now, if I wanted an exact answer, right, an exact answer which would have pi in it, I would say 6 times 6 is 36. 36 times 4 is 144, and I would have 144 pi meters squared. Now, if I wanted a number, an approximate, then we would just go to our handy-dandy calculator, we would put it in, and we would say 144 times pi gives us, if it was to 2 decimal places, we would say that this is approximately equal to 452.39 meters squared. Similarly, if we wanted to calculate volume, we would say, we'd write down our formula first, volume equals 4/3 pi r cubed, and then all we have to do once again is fill in our radius. 4/3 pi, and it's 6 cubed. And if I need an exact answer, then all I have to say is 6 cubed is 216, and I multiply that by 4/3, and I get 288 pi, again meters, but it's cubed now, it's 3-dimensional. And if I wanted an approximation to 2 decimal places, again I just take out my calculator, and I would say 288 times pi equals 904.2 decimal places, 78. 904.78 meters cubed. Spheres are actually fairly easy because there's only one dimension that we need to think about. Now, let's say though we could end up with a problem that did not give us the radius. Let's say, for example, we had a problem more like this one. And our problem, instead of giving us the radius, told us that the volume of our sphere is 10 meters cubed. Our volume is 10 meters cubed. So, of course, we'd start out by writing our formula down, which we've done. Volume equals 4/3 pi r cubed. And we know that the volume in this case that I've just given you is 10 meters cubed is equal to 4/3 pi r cubed. Then all we have to do is rearrange our formula. So in order, this was multiplied by 4/3, In order to move that to the other side, we multiply by the reciprocal. We flip that over. So we multiply by 3 over 4 to both sides, and we get 30 over 4 is equal to pi r cubed. This is pi times r cubed, so we want to move the pi on the other side, so we have r by itself. So we divide both sides by pi, and we get 30 over 4 pi is equal to r cubed. How do I get r by itself then? Well, I take the cube root of both sides. And I get that r is equal to the cube root of 30 over 4 pi. Got two parts of an irrational number there, so we're not going to get an exact number. But what we could do if we wanted an approximation, again, a calculator, what we'd have to do is start with the third root, and we want 30 divided by 4 pi, all under the radical, and we find out that r is approximately equal to 1.34 meters. Our radius, and again it's meters because we're just talking about the distance of our radius. R is approximately equal to 1.34 meters. Now the only thing that you'll find in the problems that makes these just a little bit more interesting is if we're dealing with composite figures, which we've done before. We'll leave that up there for a minute and just change our diagram. Let's say, for sake of discussion, that we wanted to have, let's say, an ice cream cone. So what's an ice cream cone made of? It's a cone with a hemisphere on top. Hemisphere, half of a sphere, hemisphere. So let's say that we have something that looks like this. There's my cone with my hemisphere sticking out the top. And let's say that my cone has a height of 5 centimeters. Sorry, not a very big cone. Has a height of 5 centimeters, and the entire cone has a height of 7 centimeters. Now, what do I need to do in order to do that? I want to know both the surface area and the volume of my composite figure. Now, I'm not going to work the numbers for you, but let's talk about how we might do it. So if we want the surface area of our figure, we have talked before about the surface area of a cone. Surface area of a cone normally has two parts, the flat part and the curved surface. Here we don't need to worry about this flat part because that's not actually part of the surface. We're only interested in the curved part. And if you'll recall, that gives me the surface area of the curved part is equal to pi times r times L, where L is this length here. Okay? And then we also have a hemisphere. So rather than the full surface area, we only want half of the surface area. So we're going to add half of the surface area, which is 4 pi r squared. And we can work that out. And we have L, we have this length here, and we also have the radius of the cone, which we should be able to figure out. The radius of the cone, excuse me, let me try again, I did miss something here. This L does not stand for the height. What does the L stand for? The L stands for the slant length. It stands for the diagonal. So we're going to have to do an extra step in this one, but we do notice we have the radius of both the cone and of the sphere, and that radius is 2. So we know that r is 2. And I'll just go ahead and write that in here, even though I didn't give it to you. We'll call that 2. And you should be able to use what? You can use Pythagoras' theorem to figure out what L is. Because we know from Pythagoras' theorem, a squared plus b squared equals c squared. In this case, a, we'll call it 2 squared plus 5 squared equals L squared. 2 squared is 4, 5 squared is 25, so 4 and 25 is 29 is equal to L squared, which means L equals the square root of 29. Okay, square root of 29. So with that number, I can figure out L. We put that in. We've already figured out R. Plug it all in your calculator, and you'll get your answer. Volume, same idea. Now, what's volume? The volume, let's start of the cone. We just want from here down, what's the volume of the cone? Well, the volume of the cone is 1/3 area of the base times the height. And then we want the hemisphere. We only need half of our sphere on the top. So that's going to be 1/2 times 4/3 pi r cubed. Now we also remember, because it's a cone, the area is what? Pi r squared. So we can simplify this to 1/3 pi r squared h plus, and then we have 1/2 times 4/3, which gives me 2/3 pi r squared. There's my simplified formula for the volume of my cone. I have the radius is 2 we talked about, the height of the cone itself is 5, and the radius again all you have to do is plug in your numbers, and you'll have the volume of your ice cream cone. And that is volume and surface area of spheres and composite figures.